Welcome everyone. I'm excited to kick off today's presentation on thermal paper 2. This is our opening slide, so I want to warmly welcome you all. Today, we'll be exploring the ins and outs of thermal paper, its applications, and recent advancements. We'll cover what makes thermal paper unique, how it's used in various industries, and some future trends to watch. Let's get started and dive into this fascinating topic. Let's take a closer look at some of the key question types we've seen over the past 10 years, focusing on both theory and numerical problems. First, we have multiple choice questions and theory questions that test our understanding of fundamental concepts. These often cover the core principles behind boiler efficiency and energy utilization. Next, we have numerical problems based on boiler indirect efficiency, which is crucial because it considers losses and gives a more accurate efficiency measure. Then, we move to energy utilization factor and heat power ratio. These are important for understanding how effectively energy is used within the system and how heat transfer compares to power input. We also encounter numerical questions related to thermic fluid heaters, which are vital in industries where maintaining high temperatures efficiently is essential. Lastly, there are problems involving heat exchanger area calculations using the log mean temperature difference, or LMTD, which is fundamental in designing and analyzing heat exchangers. Connecting all these points, the overall theme is about understanding and applying various calculations and concepts to optimize thermal systems. Recognizing the pattern in these question types helps us prepare better and grasp the practical applications in real-world scenarios. Let's talk about using steam in the process at the lowest acceptable pressure. When we refer to the lowest pressure, we're emphasizing the importance of minimizing steam consumption without compromising process effectiveness. The term acceptable means this pressure still meets the operational requirements. Using steam at the lowest acceptable pressure helps save energy and reduces operational costs. Next, the turbine heat rate is a key concept. It measures how efficiently the turbine converts fuel energy into electricity. The lower the heat rate, the better the efficiency, meaning less fuel is needed to generate the same amount of power. Improving turbine efficiency directly reduces fuel costs and enhances overall plant performance. Moving on to factors affecting wall loss in batch-type reheating furnaces. These include insulation quality, furnace temperature, and refractory material. Proper insulation minimizes heat loss, and maintaining optimal temperature reduces unnecessary energy consumption. Insulation quality is particularly critical because it directly impacts how much heat escapes through the furnace walls. Now, let's look at two proven methods of testing steam traps. The first is the temperature difference test, which involves checking the temperature difference across the trap to identify leaks or failures. The second is the ultrasonic test, where ultrasonic sensors detect the sound of escaping steam, helping us pinpoint issues accurately. These methods ensure our steam traps are functioning properly, preventing waste. Moving on to some specific equipment and cycles. The heat wheel is a regenerative heat exchanger that recovers heat from outgoing air to preheat incoming air, improving energy efficiency. The topping and botting cycle involves preheating the feedwater before it enters the boiler, saving fuel. Lastly, determining the economic thickness of insulation involves calculating the optimal insulation thickness to minimize total energy costs, balancing insulation cost against energy savings. Let's now discuss energy conservation measures. In furnaces, we can improve insulation and optimize firing schedules. For steam distribution systems, well-designed pipe insulation and leak prevention are vital. In boilers, regular maintenance and control of excess air can significantly reduce energy waste. When comparing a plate heat exchanger to a shell and tube heat exchanger, the plate type offers higher heat transfer efficiency and compactness, making it suitable for smaller spaces. Shell and tube exchangers are more robust and better for high-pressure applications. Regarding natural gas, it requires less excess air compared to solid or liquid fuels because it combusts more completely and cleanly, reducing the need for excess oxygen to ensure complete combustion. This results in better fuel efficiency and fewer emissions. In rolling mill furnaces, waste heat recovery offers major advantages like energy savings, reduced fuel costs, and lower emissions, contributing to more sustainable operations. Finally, mechanical derating reduces the capacity of equipment due to mechanical wear or limitations, while chemical derating involves adjusting performance because of chemical issues like corrosion or fouling. Both are crucial for maintaining safety and efficiency in operation. Now let's move on to slide 4. First, we look at the function of steam traps. Essentially, steam traps are vital in maintaining the efficiency of a steam system. They remove condensate, air, and other non-condensable gases from the steam lines without letting steam escape. This ensures that the system runs smoothly and efficiently, preventing energy loss and corrosion. Next, we describe the operation of regeneration for high-temperature furnaces. Regeneration is a process where heat from the flue gases is recovered and reused. Typically, it involves passing hot gases through a heat exchanger or a regeneration bed, which preheats the incoming air or fuel. This process significantly improves fuel efficiency and reduces emissions. Moving on, when selecting a biomass fluidized bed combustion boiler, there are at least 10 key points to keep in mind. These include fuel characteristics, combustion efficiency, ash handling, boiler design, emissions standards, fuel feeding system, heat transfer surfaces, operational flexibility, maintenance requirements, and cost considerations. Proper attention to these factors ensures optimal performance and sustainability. Now, let's compare CFBC, or circulating fluidized bed boilers, with AFBC, or atmospheric fluidized bed boilers. The advantages of CFBC include better fuel flexibility, higher combustion efficiency, lower emissions, and improved ability to handle larger fuel sizes. These benefits make CFBC more suitable for modern, environmentally conscious power plants. Next, I want to highlight 5 energy-saving measures. For oil-fired industrial reheating furnaces, measures include optimizing burner operation, insulating furnace walls, recovering waste heat, controlling air-to-fuel ratio, and implementing better process controls. Similarly, in steam systems, energy savings can be achieved through condensate recovery, reducing boiler blowdown, using variable speed drives, improving insulation, and maintaining equipment properly. Now, why are LPG cylinders not stored in basements or cellars? The main reason is safety. LPG is highly flammable and heavier than air, so storing it below ground level could lead to dangerous accumulation of gas in case of leaks, increasing the risk of explosions or fire. Then, why should the stack temperature of a furnace oil-fired boiler not be maintained below 160 to 170 degrees Celsius? Maintaining this temperature ensures proper combustion, complete burning of fuel, and prevents the formation of soot or carbon deposits, which could impair heat transfer and damage the boiler. Moving on, a short note on 3 equipment types. First, a plate heat exchanger, which is compact and efficient for transferring heat between 2 fluids without mixing them. Second, a multiple effect evaporator, used in desalination or concentration processes, where multiple stages improve energy efficiency. Lastly, a gas turbine cogeneration system, which combines electricity generation with useful heat recovery, maximizing overall energy utilization. Next, let's consider boiler losses. There are 6 common losses: heat loss through the flue gases, radiation losses, blowdown losses, unburned carbon in ash, sensible heat in blowdown water, and leakage losses. Finally, 2 sources of wet flue gas loss in coal-fired boilers are moisture in the coal itself and the moisture added during coal handling or processing. Both contribute to the overall moisture content in the flue gases, reducing efficiency and increasing emissions. That covers the key points on slide 4. Let's keep these concepts in mind as we see how they fit into the broader picture of efficient boiler operation and energy management. Let's start by exploring some good practices in furnace operation to enhance energy efficiency. Implementing proper insulation, maintaining optimal burner settings, regular cleaning, controlling excess air, and ensuring proper airflow are all crucial steps. These practices help reduce fuel consumption and improve overall performance. Next, we'll look at thermic fluid heating systems. These systems use high-temperature liquids instead of steam to transfer heat. They are often preferred over steam heating in certain cases because they operate at lower pressure, have faster response times, and reduce the risk of corrosion and scaling. Moving on, desuperheating is performed after pressure reduction in pressure relief valves, or PRVs, to bring superheated steam back to a saturated state. This step is essential because superheated steam can cause damage downstream, so controlled cooling ensures safety and proper operation. Now, why do we need a correction factor when estimating the log mean temperature difference, or LMTD? Well, because in many heat exchanger applications, the temperature differences are not uniform across the heat exchanger. The correction factor accounts for these variations, especially in complex or multi-stream configurations, ensuring more accurate heat transfer calculations. Let's talk about boiler preservation, wet versus dry. Wet preservation involves keeping the boiler filled with water and adding corrosion inhibitors, which prevents rusting and scale formation. Dry preservation, on the other hand, involves removing all water and applying protective coatings or inert gas to prevent corrosion during long shutdowns. Both methods are vital for maintaining boiler health during inactivity. Now, moving to reverse osmosis. This is a water purification process where pressure is applied to force water through a semi-permeable membrane. It effectively removes dissolved salts, bacteria, and impurities, providing high-quality permeate water, which is especially important in industries requiring pure water. Next, the reciprocating engine cogeneration system. This system combines a reciprocating engine with an electrical generator to produce both electricity and useful heat simultaneously. It's efficient because it utilizes the waste heat from the engine for heating processes, making it ideal for industries with simultaneous power and heat needs. Let's briefly touch on some material properties. Porosity refers to the amount of void space in a material, impacting insulation and strength. Bulk density measures how much mass is contained in a given volume, important for material selection. Pyrometric cone equivalent, or PCE, is a measure of refractory material's ability to withstand high temperatures, indicating its thermal stability. Now, what is water hammer? It's a hydraulic shock caused when a fluid in motion is suddenly forced to stop or change direction, creating a pressure surge. To prevent or eliminate water hammer, we can install air chambers, slow down valve closures, or use surge tanks to absorb the shock. Moving on to microturbines, these are advantageous in steam systems because they are compact, have quick startup times, and can operate efficiently at small scales. Trigeneration, or combined cooling, heat, and power, is an excellent example, like a system that produces electricity, provides cooling through absorption chillers, and supplies heat for heating or industrial processes, all from a single energy source. Finally, why is individual trapping preferred over group trapping? Because individual traps ensure each steam trap operates independently, reducing the risk of system failures and allowing for precise maintenance. This improves efficiency and prevents steam loss that can occur when a group trap fails. That wraps up this slide. Each of these points ties back to our overall theme of optimizing energy use and improving system reliability. Let's start by discussing the advantages of ceramic fiber in furnace applications. Ceramic fiber is highly valued because it offers excellent thermal insulation, which helps in reducing energy consumption. It also has a low thermal conductivity, meaning it effectively retains heat within the furnace. Additionally, ceramic fiber is lightweight and easy to install, which saves both time and labor costs. Its high temperature stability and resistance to thermal shock make it ideal for demanding furnace environments. Overall, using ceramic fiber enhances efficiency, saves energy, and extends the lifespan of furnace components. Next, when selecting refractory materials, there are several key parameters to consider. First is the temperature resistance, ensuring the refractory can withstand the operating temperatures without degrading. Second is the thermal expansion coefficient, which affects how the material expands and contracts with temperature changes. Third, chemical resistance is crucial to prevent deterioration due to exposure to corrosive substances. Fourth, mechanical strength determines the refractory's ability to withstand physical stresses. And finally, the installation method and cost are important factors that influence the overall selection process. Now, shifting focus to solid fuels, the significance of volatile matter cannot be overstated. Volatile matter refers to the components of fuel that vaporize at high temperatures, such as gases and tar. It plays a vital role because it influences ignition, combustion efficiency, and flame stability. Higher volatile content generally results in easier ignition and more complete combustion, but it can also lead to more soot and emissions. Understanding volatile matter helps optimize burner design and operating conditions for cleaner and more efficient combustion. Moving on to thermodynamic steam traps, their working principle is quite interesting. A steam trap is designed to remove condensate and non-condensable gases from steam lines without letting steam escape. It works by sensing the temperature or the density difference between steam and condensate. When condensate enters, the trap opens to let it out, then closes as the steam temperature rises again. This continuous cycle maintains efficient steam flow, prevents energy loss, and protects equipment from water hammer and corrosion. Now, let's briefly touch on reheaters, heat pipes, and gas turbine cogeneration systems. Reheaters are used in steam turbines to reheat the steam between turbine stages, improving efficiency and reducing moisture issues. Heat pipes are highly efficient heat transfer devices that use phase change to transfer thermal energy over long distances with minimal losses. Gas turbine cogeneration systems simultaneously produce electricity and useful heat, increasing overall plant efficiency by utilizing waste heat for heating or industrial processes. Regarding thermocompressors, these are devices that utilize heat to boost the pressure of a fluid, often in vacuum systems or desalination plants. Their main advantage is energy efficiency since they use heat, often waste heat, instead of mechanical energy, reducing operational costs and improving sustainability. Now, let's consider how positive and negative pressure affect furnace performance. Positive pressure helps contain the combustion process, improve combustion efficiency, and prevent infiltration of air or contaminants. Negative pressure, on the other hand, can lead to incomplete combustion, heat loss, and potential safety issues due to air leaks. Proper pressure management is crucial for optimal furnace operation and safety. Next, LMTD, or log mean temperature difference, is a fundamental concept in heat exchanger design. For example, in a counterflow heat exchanger, where hot and cold fluids move in opposite directions, the LMTD helps determine the heat transfer rate. It's calculated based on the temperature differences at both ends, providing a more accurate measure than just the temperature difference at one point. This helps in designing efficient heat exchangers that maximize heat transfer while minimizing size and cost. Moving on to heat wheels, heat pumps, and temperature correction factors. A heat wheel is a rotary heat exchanger that transfers heat between incoming and outgoing air streams, improving energy recovery. Heat pumps are devices that transfer heat from a cooler area to a warmer one, using refrigeration cycles to provide heating or cooling efficiently. Temperature correction factors are used in calculations to account for variations in temperature, ensuring design and operation are optimized under different conditions. Now, let's discuss heat exchanger effectiveness. It measures how well a heat exchanger performs relative to an ideal exchanger. An effectiveness of 100% means the heat transfer is perfect, while lower values indicate less efficient performance. Knowing this helps in assessing whether a heat exchanger is suitable for a particular application or if improvements are needed. Next, pinch technology offers significant benefits in process industries. It involves optimizing heat integration by identifying the pinch point, the temperature where heat exchange is most effective. By minimizing unnecessary heating and cooling, it saves energy, reduces costs, and improves sustainability. Applications include refining, chemical processing, and power generation, where energy efficiency is critical. Finally, let's define some important terms. Cold crushing strength refers to the maximum compressive stress a refractory material can withstand at room temperature before failure. Creep is the slow, permanent deformation of a material under sustained stress at high temperatures. Reversible thermal expansion is the expansion and contraction of materials with temperature changes, which is reversible and does not cause damage if within limits. Refractory under load refers to refractory materials subjected to mechanical stresses during service, where their strength and stability are vital for safe operation. That covers the key points for this slide, connecting the concepts to the broader theme of efficient and sustainable thermal systems. Natural gas requires less excess air compared to solid or liquid fuels. This is mainly because natural gas is in a gaseous form and is lighter than air. Due to its gaseous nature, it mixes with air very readily, allowing for intimate mixing of oxygen and fuel. This efficient mixing helps achieve complete combustion with a smaller amount of excess air. Additionally, natural gas burns cleanly. It doesn't produce smoke or soot, and it has no sulfur content. Its lighter weight also means that in case of a leak, it disperses easily into the air, reducing hazards. Unlike solid or liquid fuels, natural gas doesn't produce ash, which simplifies the combustion process. On the other hand, solid and liquid fuels need extra steps before they can burn efficiently. Solids must be pulverized into uniform sizes, and liquids need to be preheated and atomized properly. These processes ensure better mixing with air, but they also mean that more excess air is necessary to achieve complete combustion. So, in essence, the key reason natural gas needs less excess air is because of its gaseous, lightweight nature and its ability to mix thoroughly with air, making the combustion process more efficient and cleaner. Let's start with density. Density is essentially the ratio of the mass of fuel to its volume at a standard temperature of 15 degrees C. We measure this property using an instrument called a hydrometer. Knowing the density helps us perform accurate quantity calculations and also assess the ignition quality of the fuel. The units for density are kilograms per cubic meter, or kg/m3. Moving on to specific gravity, this is the ratio of the weight of a certain volume of oil to the weight of the same volume of water at a given temperature. Since water has a specific gravity of 1, the specific gravity of the fuel tells us how heavy or light it is relative to water. And because it's a ratio, it has no units. We typically measure specific gravity with a hydrometer as well. Now let's talk about viscosity. Viscosity measures how resistant a fluid is to flow internally. Think of it as the fluid's thickness or stickiness. Importantly, viscosity depends on temperature. Generally, it decreases as temperature rises. So, any numerical value for viscosity isn't meaningful unless we specify the temperature. We measure viscosity in units like Stokes or centistokes using a device called a viscometer. Sometimes, viscosity is also expressed in other units like Engler, Seybolt, or Redwood seconds. Why is viscosity important? Well, it directly influences how much preheating the fuel needs for proper handling, storage, and atomization. If the oil is too viscous, it becomes difficult to pump, hard to ignite, and tough to operate. Poor atomization caused by high viscosity can lead to carbon deposits on burner tips or walls, which is definitely undesirable. To prevent that, preheating becomes necessary to ensure the fuel atomizes properly, leading to cleaner combustion and better efficiency. In industrial applications, liquid fuels such as furnace oil and LSHS are predominantly used because of their suitability for large-scale processes. Finally, it's worth noting that fuels come in various forms: liquid, solid, and gaseous, and the choice depends on factors like availability, storage, handling, pollution considerations, and the overall cost. Selecting the right type of fuel is crucial for optimizing performance and minimizing environmental impact, fitting into the broader theme of efficient and sustainable energy use. Let's discuss ash content first. The ash value essentially tells us about the inorganic material present in the fuel oil. For distillate fuels, the ash levels are usually negligible, which is good because it means fewer deposits during combustion. However, residual fuels tend to have higher ash content because they contain more of these inorganic ash-forming constituents. These can include compounds of sodium, vanadium, calcium, magnesium, silicon, iron, aluminum, nickel, and others. Now, the typical ash value ranges from about 0.03 to 0.07%. While that might seem small, excessive ash in liquid fuels can cause real problems. For example, it can lead to fouling deposits in the combustion equipment, which reduces efficiency and increases maintenance. Moreover, ash has an erosive effect on burner tips, damaging the refractory materials at high temperatures, and it can cause high-temperature corrosion and fouling of the equipment. So, controlling ash content is crucial for maintaining equipment longevity and efficiency. Moving on to carbon residue, this indicates how likely the oil is to leave behind a carbonaceous solid residue when it's heated. Think of it as a measure of how much deposit the oil might form on hot surfaces, like burners or injection nozzles. Residual oils often contain a carbon residue of 1% or more, which can be problematic because these deposits can impair combustion and reduce efficiency. Finally, let's talk about water content. When furnace oil is supplied, its water content is usually very low, often less than 1%, because at the refinery the product is handled hot, which helps minimize water presence. However, water can be present in free or emulsified forms, and this can cause serious issues during combustion. For instance, when water contains dissolved salts, it can damage inside furnace surfaces and lead to corrosion. It can also cause spluttering at the burner tip, which can extinguish the flame or lower the flame temperature. All these effects can compromise the combustion process and the overall operation. So, in summary, monitoring ash, carbon residue, and water content are all vital for ensuring the fuel performs well and doesn't cause damage or inefficiency in the system. Heavy fuel oils are best pumped using positive displacement pumps because they are able to get the fuel moving effectively even when it's cold. This type of pump maintains a steady flow regardless of viscosity changes, which is crucial for heavy fuels. When it comes to circulation gear pumps running on LDO, you can generally expect between 7,000 to 10,000 hours of service if properly maintained. Diaphragm pumps, on the other hand, tend to have a shorter service life, but they are easier and less costly to repair if something goes wrong. It's a trade-off between longevity and maintenance convenience. Now, I wouldn't recommend using centrifugal pumps for heavy fuel oils. As the viscosity increases, the efficiency of centrifugal pumps drops sharply, and they require much more horsepower to operate. That makes them less reliable for heavy fuels. For lighter fuels, however, centrifugal or turbine pumps are the better choice. They handle lower viscosity efficiently. When you need higher pressures, piston or diaphragm pumps are more suitable because they can deliver the required force effectively. And here's a critical point to remember. Losing even 1 drop of oil every second can add up quickly, over 4,000 liters lost in a year. That's a significant cost, so ensuring tight seals and proper maintenance is essential to prevent unnecessary losses. Normally, D, E, and F coal grades are the ones available to the Indian industry. The most commonly used coals here are bituminous and subbituminous coal. When we look at Indian coal based on its calorific value, we see a clear gradation. Now, from a geological perspective, anthracite is the oldest type of coal. It's quite hard and mainly made up of carbon, with very little volatile content and almost no moisture. It's known for its high carbon content and energy density. On the other hand, lignite is the youngest coal in geological terms. It's softer and contains more volatile matter and moisture, but has lower fixed carbon. Speaking of fixed carbon, this is simply the carbon that exists in its free state, not combined with other elements. It's a key indicator of coal's energy potential. Volatile matter, meanwhile, refers to the combustible components in coal that vaporize when we heat it. These volatile components are important because they influence how coal burns and its overall energy release. Lastly, coal is generally classified into three main types: anthracite, bituminous, and lignite. Each has unique characteristics, and understanding these helps us choose the right type for different industrial applications. Connecting this to our overall theme, knowing the properties and classifications of coal helps us optimize its use in the industry, ensuring efficiency and sustainability. Let's start by talking about the flash point of a fuel. The flash point is essentially the lowest temperature at which the fuel can be heated so that, when an open flame is passed over it, the vapor gives off flashes momentarily. For furnace oil, this temperature is typically around 66 degrees Celsius. This is a critical safety measure because it tells us the temperature at which the fuel becomes flammable in the presence of an ignition source. Moving on to the pour point, this is the lowest temperature at which the fuel will still pour or flow when cooled under specific conditions. Think of it as a rough indicator of how cold the fuel can get before it stops flowing easily. It's especially useful for understanding how the fuel behaves in cold weather and whether it will be pumpable without issues. Next, let's discuss specific heat. This is the amount of energy, measured in kcal, needed to raise the temperature of 1 kilogram of oil by 1 degree Celsius. The specific heat varies between 0.22 and 0.28 kcal per kg per degree Celsius, depending on the oil's specific gravity. Why does this matter? Because it determines how much energy, whether from steam or electricity, is required to heat the oil to a desired temperature. Light oils tend to have a lower specific heat, meaning they heat up more easily, while heavier oils require more energy to reach the same temperature. Finally, let's look at calorific value, which tells us how much heat or energy a fuel produces during combustion. This can be measured as either the gross calorific value or the net calorific value. The key difference is that the gross value assumes all the water vapor produced during combustion is fully condensed, releasing its latent heat. The net calorific value, on the other hand, assumes the water leaves with the combustion products without being fully condensed, so it's a more realistic measure for practical purposes. When comparing fuels, it's best to focus on the net calorific value because it provides a more accurate picture of the usable energy. It's worth noting that the calorific value of coal can vary quite a bit depending on factors like ash and moisture content, as well as the type of coal. In contrast, the calorific value of fuel oil is generally more consistent, making it easier to predict its energy output reliably. One important disadvantage of using sulfur in fuel oil is the risk of corrosion. This happens because during and after combustion, sulfur reacts to form sulfuric acid. This acid can then condense in cooler parts of the system, like the chimney or stack, as well as in the air preheater and economizer. This corrosion can lead to significant damage over time, so it's a critical factor to consider. Now, when we talk about sulfur content in fuel oil, it mainly depends on the source of the crude oil. The refining process also has an influence, but to a lesser extent. Typically, residual fuel oil, which is often used as furnace oil, contains about 2 to 4% sulfur. This variation can impact both environmental emissions and equipment maintenance. Switching gears a bit, let's look at how we can estimate the energy content of fuel. The gross calorific value, or GCV, is an important measure. It tells us the total energy released when the fuel is burned completely, including the energy from condensing water vapor. We can calculate GCV using this formula. GCV equals the net calorific value, or NCV, plus 584 times the sum of hydrogen percentage and moisture percentage divided by 100. Here, 584 is the latent heat associated with water vapor at the partial pressure during combustion. So, understanding both the sulfur content and the calorific value helps us optimize fuel use, manage corrosion risks, and reduce environmental impact. All key themes in efficient and sustainable energy management. Let's discuss why steam should be used at the lowest practicable pressure for indirect process heating. When we look at the steam tables, we see that the latent heat of steam decreases as the pressure increases. Now, since it's the latent heat that actually participates in the heating process in an indirect system, we want to maximize it. And the best way to do that is to operate at lower steam pressures, because the latent heat is higher there. It's also important to remember that steam is generally generated and distributed at the highest possible pressure, but then used at the lowest pressure feasible. This way, we retain the higher latent heat during the transfer process, making the system more efficient. However, there's a trade-off. Lowering the pressure also lowers the temperature of the steam, which reduces the temperature differential that drives heat transfer. This means heat transfer becomes slower, and processing times can increase. In some equipment, especially those with high fixed losses like large drying cylinders, this can even lead to increased steam consumption because of the longer processing time. But in certain industries and specific equipment, operating at lower pressures can still be beneficial. You can save on steam consumption without significantly impacting production time. So, the key takeaway is that there's a practical limit to how low we should go with steam pressure. We need to find that balance, depending on the equipment design, where we can operate at the lowest possible pressure without sacrificing either production efficiency or excessive steam use. Let's discuss why LPG cylinders should not be stored in basements or cellars. LPG is mainly a mixture of propane and butane, and both of these gases are denser than air. This means that if there's a leak, the vapor tends to flow along the ground, moving into drains or sinking to the lowest points around. And here's the critical part. These vapors can ignite even at a distance from the source of leakage. So even small leaks can produce a large volume of flammable vapor, creating a serious hazard. To prevent this, it's essential to have adequate ground-level ventilation in storage areas. That's why storing LPG cylinders in cellars or basements, which typically lack proper ground-level ventilation, is highly unsafe. Now, moving on to the stack temperature of furnace oil-fired boilers. It's important not to maintain the stack temperature below about 160 to 170 degrees Celsius. The reason for this is related to sulfur content in the fuel. When the temperature drops too low, below that range, sulfur can condense and form sulfuric acid inside the chimney or stack. This process is called sulfur dew point corrosion. The formation of sulfuric acid is problematic because it can cause significant corrosion, especially on cooler surfaces like the chimney lining, air preheaters, or economizers. Maintaining the right temperature helps prevent acid formation, protecting the equipment and ensuring safe, efficient operation. This ties back to the overall theme of safety and efficiency in our operations. Let's discuss the role of the 3 T's in achieving efficient combustion. The main goal of good combustion is to release all the heat from the fuel, and this can be effectively managed by controlling these 3 critical factors, or T's. First, we have temperature. It needs to be high enough to ignite the fuel and keep the combustion process going. Without reaching that ignition temperature, the fuel simply won't burn properly. Next, turbulence. This is all about the intimate mixing of fuel and oxygen. When the fuel and air are thoroughly mixed at the molecular level, combustion becomes much more complete and efficient. Turbulence helps achieve this ideal mixing by creating a chaotic flow that encourages molecules to interact more thoroughly. And finally, time. The fuel-air mixture must stay in the combustion zone long enough for the chemical reactions to be fully completed. If it moves through too quickly, some of the fuel might not burn completely, wasting energy and reducing efficiency. To sum up, for sustained and efficient combustion, the fuel-air mixture needs to reach a temperature above ignition point, be well mixed through turbulence, and remain in the high-temperature zone long enough for complete combustion to occur. Remember, in practice, ensuring these 3 T's are properly managed, whether through design or operation, is key to maximizing heat release and overall efficiency in a combustion system. Let's explore the difference between the flash point and the pour point of a liquid fuel. The flash point is essentially the lowest temperature at which the fuel, when heated, produces enough vapor to ignite momentarily when an open flame is passed over it. It's a critical safety parameter because it indicates how easily the fuel can catch fire at certain temperatures. On the other hand, the pour point is the lowest temperature at which the fuel can still pour or flow when cooled under prescribed conditions. Think of it as a practical measure of how cold the fuel can get before it stops flowing and becomes difficult to handle. It gives us an idea of the fuel's pumpability in cold environments. Now, moving on to solid fuels, specifically, the significance of volatile matters in combustion. Volatile matters in coal include gases like methane, hydrocarbons, hydrogen, carbon monoxide, and even incombustible gases such as carbon dioxide and nitrogen. These volatile components are important because they essentially act as an index of the gaseous fuels present in the coal. Typically, volatile matter makes up about 20 to 35% of the coal. Having a higher volatile content usually means the flame length increases, and it becomes easier to ignite the coal. This is because these gases ignite more readily, aiding in a smoother combustion process. Additionally, volatile matter influences the design of the furnace, setting minimum limits on the height and volume needed for effective combustion. It also impacts secondary air requirements, helping with proper air distribution, and influences secondary oil support in certain combustion setups. Overall, understanding the volatile matter helps us optimize combustion efficiency and safety, ensuring we design and operate our systems effectively. Let's start by looking at the difference between a water tube boiler and a fire tube boiler. In a fire tube boiler, the combustion gases are inside small fire tubes, which are bundled together. The water to be heated is outside these tubes, surrounding them. Conversely, in a water tube boiler, the water flows inside the tube bundles, and the combustion gases pass around these tubes. This fundamental difference influences how each boiler handles pressure and capacity. Now, regarding the pressure range where water tube boilers have an advantage over fire tube boilers, this is typically at steam pressures above 20 bar and larger capacities. The reason is quite practical. If we try to build a fire tube boiler for high pressure, the shell would need to be extremely thick and heavy to withstand that pressure. This makes fire tube boilers less feasible at higher pressures and capacities. Water tube boilers, on the other hand, are designed to handle these conditions more efficiently because the water is inside the tubes, which can be made thinner and stronger, making them more suitable for high-pressure applications. This distinction is important because it connects to the overall theme of choosing the right boiler type based on operational needs and safety considerations. Let's take a closer look at packaged boilers and what makes them special. As the name suggests, a packaged boiler comes as a complete, ready-to-install system. Once it arrives at the site, all that's needed are the connections for steam, water pipework, fuel supply, and electricity to get it up and running. This streamlined setup makes installation quick and efficient. Most packaged boilers are of the shell and fire tube type. This design helps achieve high heat transfer rates through both radiation and convection, making them very effective for various applications. Now, what are some of their key features? First, they have a small combustion space, which means they can produce a high heat release rate. This results in faster evaporation, so the boiler can generate steam quickly when needed. Next, they contain a large number of small diameter tubes. These tubes enhance convective heat transfer, ensuring the heat from combustion is efficiently transferred to the water. Another important aspect is the use of forced or induced draft systems. These systems help improve combustion efficiency by ensuring a steady, controlled airflow through the boiler. And finally, the number of passes, meaning how many times the hot gases pass through the boiler, also plays a crucial role. More passes mean better overall heat transfer, increasing efficiency. Classifying these boilers based on the number of passes, the combustion gases go through the first pass in the combustion chamber, and then may pass through 1, 2, or even 3 sets of fire tubes. This design flexibility allows us to optimize the boiler's performance based on specific needs. So, in essence, packaged boilers offer a compact, efficient, and easy-to-install solution, with features that maximize heat transfer and operational efficiency, aligning perfectly with our goal of reliable steam generation. Now let's discuss what clinker is. Clinker is essentially a rough, hard, slag-like material that forms during the combustion of coal. It occurs because the ash in coal has a low fusion temperature, which causes it to melt and then solidify into this clinker. The key components in the ash, such as silica, calcium oxide, and magnesium oxides, contribute to this low melting point. There are several factors that lead to clinker formation in a stationary grate coal-fired boiler. First, a low ash fusion temperature makes it easier for the ash to melt and form clinker. Second, if the coal has uneven particle sizes or a higher proportion of fines, it can cause uneven burning and ash deposits. Third, combustion without raking the coal bed can lead to uneven heat distribution and clinker buildup. And lastly, the use of preheated air for combustion can raise the temperature and promote clinker formation. Now, shifting gears a bit, let's look at some energy conservation opportunities within a boiler system. First, controlling stack temperature is crucial because high stack temperatures indicate wasted heat. Second, preheating feed water with an economizer recovers waste heat and improves efficiency. Third, managing excess air helps reduce heat losses and improves combustion efficiency. Fourth, preheating combustion air further enhances energy savings. Fifth, automatic blowdown systems help remove impurities and maintain optimal boiler operation. Sixth, reducing scaling and soot buildup minimizes heat transfer losses. Seventh, minimizing radiation and convection heat losses through insulation and proper design conserves energy. Eighth, using variable speed control for blowers and pumps allows for better adjustment to load demands, saving energy. Ninth, ensuring proper boiler loading prevents inefficiency caused by operating under or over capacity. And finally, addressing incomplete combustion and unburnt losses is essential to maximize energy use. By understanding these factors and opportunities, we can significantly improve boiler efficiency and contribute to overall energy conservation.